Welcome to the 7th lecture of combinatorics. Today we will continue with bijective proofs, right? That's all. So, this is like as we have seen, it's a special case of the division principle where our function between the two sets is a bijection. Bijection means a one-to-one correspondence, right. So, if it is a function from T to S, then every member of S has exactly one pre-image. So, it is not possible that two different members of T get mapped to the same member in S, right. So, then and also every member in S has a pre-image. This is the bijective. The point is, if you can establish a bijective function, bijection between the two sets, then both sets should have the same cardinality. Whichever set is easier to count, we will count, and then we can infer that the other set also has the same cardinality. So, in the last class we started with an example where we counted the number of subsets of an n element set. We noted that there is a bijection between this set, namely the family of or the set of subsets of an n element set and the n length binary strings, and it was easier to count n length binary strings. It was 2 raised to n. Therefore, we also inferred that the number of subsets of a n element set is 2 raised to n, right. The next question we considered was this: for any positive integer n, the number of divisors of n that are larger than root n is equal to the number of divisors of n that are smaller than root n. We considered some examples in the last class, and so that it is for small numbers it is indeed holding. For instance, I can take one more example. For instance, let us take 49. I am taking a perfect square to make it to avoid, it is not necessary that I have to take a perfect square. So, its root is 7 here. I am interested in the divisors of 49 below 7. How will I find? This is 1 is a divisor, 2 is not, 3 is also not a divisor, 4 is not, 5 is not, 6 is not, 7 is a divisor. So, but then so this is similarly, if you above 7 you can only see 49 itself, right. So, here and here we will have correct. So, here the number here and number here. So, just one here, the number of devices above 7 is equal to the number of devices below 7, right. That is what we see. So, of course, for small numbers this seems obvious, but is it true that for any number n this is true? Given any number n, so the number of devisors of n, so devisors of n, the number of devisors of n below root n, strictly below root n, this number, is it equal to the number of devisors of n strictly above root n? This is what we want to see. What we do is, let us consider this as set S, and we will consider this as set T, and then we will establish a bijection F between S and T, right. So, we want a bijective function F from S to T. How do we do this thing? The point to note is that if 1 is the divisor of n, then n itself is also a divisor. So, if 2 is a divisor, then n by 2 is also a divisor of n, because 2 into n is equal to n, right. Similarly, if d is a divisor, then n by d is also a divisor. This is what we are going to use in this bijection. For example, if you take the divisors of 24, for instance, right. If you take 1, 24 is also a divisor, 2 is a divisor, then 12 is also a divisor, 2 into 12 is equal to 24, see. So, similarly 3 is a divisor, so then 8 is also a divisor, right, because 3 into 8 is equal to 24, right. If 4 is a divisor, then 6 is also a divisor, 16, because 6 into 4 is 24. And now the point is, if any number d is taken and if it divides 24, then 24 by d also is an integer and that divides 24, right. So, in general, if d is a divisor of n, d divides n, then that implies n by d is a positive integer and then that divides n, right. So, we can say that if d is a divisor, n by d is a divisor. So, our bijection is like this, f of d is equal to n by d for any for d element of S, right, where S is the set of divisors of n strictly below root n, right. So, we can map it to this. Now, we can check that this is a function first, what all things we have to check that that is a function. For every divisor we do get this one, yes, we do get, because if d is a divisor, indeed n by d exists, because you can divide n by this d and that is an integer, that is why it is called a divisor, right. Now, for a given divisor of n below root n, this number is also uniquely defined, n by d only, right. So, therefore, it is indeed a function, right. Now, what we have to check is, it is this function is indeed a bijection. How do we check? So, we go to the set T, namely the divisors of n strictly above root n, right, divisors of n strictly above root n we take, this is this. So, now you take any k, right. So, we can, okay, we also had to note that. So, this n by d belong to t, right, when we say, because our function is defined from S to t. So, you see that this d is strictly less than root n, then n by d has to be strictly bigger than root n. Why? Because so when d is root n itself, n by d will become equal to root n. If d was smaller than root n, then n by d has to be bigger than root n. That is why this is indeed a number which is a positive integer bigger than root n, right. Similarly, here if you take any k which is bigger than root n and a divisor of n, if you consider n by, so this where it came from, right. So, this is from n by t for some right, for some t, that is what, then that is so we want to find out which is the t. So, t is equal to definitely n by k. Same way, since k is greater than root n by k has to be less than root n, right. So, t will be a number which is less than root n, and definitely this t is a divisor of n, because if I divide n by t, then we will get indeed this k integer, right. So, therefore, that is there is a pre-image and there is indeed one pre-image, right. So, because there is a unique one we are getting, it is quite easy to see. So, therefore, we have established a bijection f from S to T here, right. So, therefore, the cardinality of S has to be equal to cardinality of T the way we want it. The number of divisors of n strictly below root n is equal to the number of divisors of n strictly above root n. Okay. So, now you can see that why is it useful? Of course, this is we are just not telling how many divisors are there for n below root n or above root n, but then we are saying that both these numbers are indeed same, that is a number of devices below root n and above root n. Sometimes it can be useful, for instance, you can consider 10,000, right, and then you ask somebody maybe in a school kid to write down all the divisors of 10,000 which is greater than 100, suppose if you ask, right. 100 is not 100 is the square root of 10,000, right. So, then he may do like this, he may check whether 101 is a divisor of 10,000 or not, then he says no, 102 he tries no. So, like that he may try. So, when he reaches 200 he may write yes. So, and he writes down okay 200 I got 1. So, like that he can keep listing things, but how many times he has to do this thing? So, he has to do for all the numbers below 10,000, that means 9999, or maybe including 10,000 for that matter, 10,000 that matter minus say 100, this many numbers you have to do, that means 9900, right, 9,900 numbers he has to try. So, you may say that okay, why should I go above 5,000, because I know that nothing above 5,000 will divide 10,000. So, maybe even then I have to do 4,900 times this thing, right. So, assuming that so you are clever enough to identify that, yes, you may end up doing 4,900, right. But on the other hand, if you had used our theorem, that means the number of divisors of 10,000 above 100 will be equal to the number of divisors of 10,000 strictly below 100, then you could have done like this. You just check whether 1 is a divisor, yes, 2 is a divisor, yes, 3 is a divisor, no, 4 is a divisor, yes. So, like that you could have listed the first 99 numbers which are strictly below 100, and then we could have done with it. And just 99 checks, 99 tests instead of that 4,900 or 9,900 tests, right. So, this is a much better thing to do, right. So, of course, it need not be a school boy, it can be a computer. You may be writing a program for this to find out how many divisors are there for a number n which is above root n, right. Then you may write say for root n k equal to root n plus 1 to n do something like that, you may write saying that testing whether k is a divisor of n, if k is a divisor of n then output k, something like that. But then you have to do it for n minus root n times, right. And if n is for instance a very big number 10 million, so this can be very large. But on the other hand, 10 million, how much is 10 million? So, this say 10 raised to, let us say 10 raised to 3. So, 10 raised to 6 is a million, right. So, 10,000, right, and 10,000, 1 lakh, 10 lakh, this is a million, and then 10 million is one more 0. So, I do not know whether its root is, how much is its root. So, you can keep say 1 0 for every 2 zeros here, okay, something above 10,000, so 1,000, right, maybe yeah, into some 3,300 or something like that, right, 330, something like that. Maybe you can put one more 0 here and make it a little bigger number, that means 1 2 3 4 8, 10 raised to 8, consider 10 raised to 8. So, then this is only 10,000, right. So, suppose the computer has to run. So, this minus this times, this is almost this number and this many tests it has, it may take long time, but on the other hand, okay, of course, it depends on how fast your computer is. So, but still if you are clever enough to do it from k equal to 1 to root n minus, okay, assuming that root n is integer, root n minus 1 or root n floor, and then check the same thing. So, you may do much faster, because this root n here is much smaller than n minus root n, because n minus root n is almost like n, right. So, for big enough n, while root n is much smaller. So, this is one thing. Of course, when I always talk, suppose if you want to find how many devices are there for n which is above root n. It need not be the question, sometimes it can you can simply get the question, so how many devices are there for n, right. So, you can do the number of devices below root n and multiply it by 2, because above root n equal number of devices will come, and then we can test whether root n itself is a divisor of n or not. So, then that also indicates a very interesting thing. So, what kind of numbers have odd number of devices. For instance, 6, if you consider its number of devices is 1, 6, 2, 3, it has an even number of devices, right, 4 devices. But on the other hand, if you consider 9, it has 1, 9, 3 devices. This is an odd number of devices, right. So, on the similarly, if you take 24, if you have 1, 24, 2, 12, 3, 8, 6, 4, this many devices, 4 plus 4, 8 devices, right. So, now some numbers have even number of devices, some numbers have odd number of devices. What kind of numbers have odd number of devices? Which is, it's easy to see that depends on root n. If root n was an integer, then there will be odd number of devices, because if you consider the number of devices below root n, that is exactly equal to the number of devices above root n, and when you count the number of total number of devices, this plus this will add, because these are equal numbers, that is 2 times this number here. So, that will be an even number, and then finally, we test whether this is a divisor of n or not. If this is a divisor, then that even number here 2 into this number, say t, 2t plus 1 will be the total number of devices, which is odd. So, if root n is a integer, that means n is a perfect square, then it will have odd number of devices. On the other hand, if root n was not an integer, it was something like 12.345, something like that, then definitely we do not have root n as a divisor of n, we just have 2t, that means an even number of devices, right. So, that way we can figure out, right, easily what kind of numbers have even number of devices and odd number of devices. It is just a matter of looking whether n is an odd number or even number. Okay. So, now okay, next question we will consider is this is also a common kind of problem question which is considered in combinatorics. So, here we talk of something called northeastern paths. So, what is northeastern paths in a grid? So, consider a grid like this, something like this. Yeah, it can be any length, but I will draw like this. It is a grid like this. Okay, you can draw further, or here also you can draw further, right. So, this is the point 0, 0, this point. Okay. And then suppose you can see, you can assume that this is some kind of roads, right. Some it's a collection of roads. These lines correspond to some roads, and they are like this. They are somehow arranged in a maybe when somebody created a new city, modeled the city as a grid, like all the roads in the city is like a grid. So, this is a 0, 0 point. You always say that I want to reach this point, say, or this point or this point, something like that. But suppose there is a restriction that you can either drive forward. So, So, usually you can say this is the east direction, right, forward east direction, or you can drive north direction, right. So, either east or north you can go, you can never go backward, or you can never go downward, right. This is the restriction. Now, the point is to the question we ask is like this: how many ways you can, there are how many routes to reach from 0 0 to certain point. So, the first question we ask is, suppose this is a point say k comma n minus k. See, because I write like this, it is very clear what I mean, it will give us a little bit of hint, but then I can take some numbers like so in the now question k n minus k. So, I put n equal to 10 and k equal to 4, and then right. So, this is 4 6. So, I am interested in reaching 4 6 1 2 3 4 1 2 3 4 5 6. So, 1 2 3 4. So, 4 6 here 1 2 3 4 5 6. So, this point, this is 4 6. Okay. Suppose I want to reach from here to here, right. The question, and I am driving the car, the rule is that I can drive eastward or northward. So, that is the, so we are only interested in northeastern paths. And how many routes are there? So, for instance, I can, one example is I can drive like this simply, and then see straight here, and then I will go straight here. But if I had taken one step further, I will never reach here, because to reach here I will have to come back, right. So, that is not allowed. Or I could have taken a more zigzag path like this, see, like this, and then gone upward, right. Or this, if I could have just taken this path, and here I could have taken as, this is a different path. So, the path is different, if it is not entirely the same path, then we say that two paths are different, right. So, the question is how many such paths I can take from to reach from 0 0 to 4 6. In general, we write this 4 6 k equal to 4, and we write n minus k equal to 6, and the sum of these two 10, right, that is equal to n. We want to reach from k to n minus k. So, why do I write like that? So, the reason is that to reach 4 6, you know, whatever I do, in whichever, however clever I become, I have to take 4 eastern directions. I mean 4 units I have to see one, say you can say that this is 1 kilometer. So, 1 unit here, 1 unit distance, 4 units I will have to travel towards east, because if I travel only 3 units, then I will reach maximum up to here, right, up to here. I will be, see, vertical, I mean in the north direction, how much ever I travel, I will be before this line, right. I mean I will never cross this line right here, right. So, therefore, I will have to take 4, and I have to take 4, because I cannot take 5. If I take 5, I will cross this line and I will never be able to come back, right. So, to reach 4 6, I have to take 4 units, say 4 kilometers east. I have to drive 4 kilometers east. Somehow, when I do is unimportant, before I reach there I have to do that exactly 4 kilometers. Similarly, to reach 4 6, I have to drive 6 kilometers north. I can do it, I mean 1 kilometer east, then 1 kilometer north, 1 kilometer is like this, 1 kilometer north, 1 kilometer east, 1 kilometer north, like that. Or I could have done 2 kilometer north, then 1 kilometer east, then another 2 kilometer north, then now 2 kilometers east. So, I have finished 1 plus 2, 3 kilometers, 1 more kilometer north, but here 2 plus 2, 4, and another 2 here, right, then I could have taken this, I will reach there, right. So, but in whichever way I do not know, I should have taken these total 4 kilometers eastwards somewhere. Similarly, I should have taken this 6 northward units at some point of time, right. So, the question is, and total, so therefore, total how many units I should take? I should take 4 eastward units and then 6 northward units. So, total 10 units I should take, I should move, right. And then out of the 10, 4 is east. Now, how do I design my paths? So, one possibility is to try drawing all possibilities. It is not so easy, because it is not easy to count, because you see, you can try, see here when I reach here I have 2 possibilities, then from when I reach here I have another 2 possibilities, like that I can count, but then some places the 2 possibilities are right. So, the here, so yeah, right, here we have 2 possibilities like that, right. And then right, even if we count, so at some point of time what will happen here, when I reach here there is only one possibility, right. So, we have to do some adjustment for that. So, right. So, one can try counting it in other words, but a clever way of looking at it is, as I have mentioned, is that I have to anyway take 4 kilometers eastward. The question is, out of the 10 units I take, I just arrange them like the first unit, this is the first unit, second unit, third unit, fourth unit, and then finally 10th unit. Out of this I can say that I will take the third time, I will take the east, right, and then say fourth time also I will take the east, 10th time I will take the in the 10th step I will take the east, maybe again also during the 7th step I will take the east. So, I will take the east, right. So, so that if I have decided these are the 3 times I take east, then other places I will have to put north, right, north, 6, 5, 6, north, like this, right. So, 6 north will come that way, 7, 8, 9, 8, 9, north and north. So, there this is the way. So, once you fix my east, then the north will automatically fixed. So, for instance, for this one, so I see that the first step has to be north. So, this will be like this, the second step has to be north, I will go northward, second step also, as if the driver is looking at this chart and moving, and the third step is east. So, he will take this step, and then fourth step is again east, he will take this step, and then the fifth step is north, he will take this one, and the sixth step is also north, he will take this one, seventh step is east, he will take this one, eighth step is north, and then 10th step is again north, and sorry, 9th step is again north, and 10th step is east. So, he is reaching there, right. And now, what I am going to do is, so I am claiming that this kind of chart, this kind of a pattern that you have written, something like N, N, E, E, N, N, E, N, N, E. So, there is an N and E chart, there are 10 letters here. So, if you count the number of strings here, which I can make like this, these strings corresponds to different paths, and each path will correspond to this. In other words, I will set up a bijection between the northeastern paths from 0, 0 to 6, 4, and the 10 letter sequences using E and N with 4E and 6N, something like this, N, N, E, N, N, E, this kind of sequences. Why is it so? So, because as I have shown you, so I first say that this is a function, this is the function we map it. So, we look at a path, we just write down along the path, we will go and write down the sequence. So, this is n e n e n e like that for every path. For instance, this path I can write n e n, right. So, we will be able to write down one sequence like that, and you can clearly see that every path will get a sequence, right, and for each path just one sequence will come. So, it is indeed a function, and then we want to verify that it is a bijection. Although take any sequence from that given a sequence, we can cook up the way I have shown. Following the sequence, I can, so the car driver can look at the sequence and decide the route, and the route is unique, right, and therefore, there is one path according to one sequence, and there is indeed one sequence, because 4 steps if he takes, because in the sequence there are exactly 4 E's, and if you take whichever time at what step, it does not have to worry. If he takes 4 eastern steps and then 6 northern steps, he has to reach this 4n, because out of 10 units he has moved already 4 kilometers northward and 6 kilometers southward. So, therefore, he will be reaching this if you follow that. So, that is indeed a bijection between this and this, right, and then we see that this number and this number is same. Now, this number, what is this number? This number is actually there are 10 positions here, So, we have to put east in 4 positions, right, and the remaining position automatically will be filled by n. So, we just have to select the positions to set our ease, fit our ease in, right. So, out of 10 positions, how many 4 positions are to be selected, that is 10 choose 4, right. This number, cardinality of this number will be, this set will be 10 choose 4. So, that is naturally 10 choose 4. So, you could also have selected the northern paths. So, that would be n 10 choose 6, right. So, we will soon see that these are going to be the same. So, that will or in other words we can say. So, suppose for a general problem, suppose if I want to go from 0 0 to 0 0 to k n minus k, right. So, in our example k was 4, this was 6. So, then that means out of n units we have to travel k units east and n minus k units north, right. So, it is just a question of fixing k e's in the sequence of n, that is n choose k. So, the number of paths from 0 0 to this is actually n choose k, right. That is what we just proved, and as we notice the n choose k will be equal to n choose n minus k, because then the same sequences can be obtained by fixing n's rather than e's. So, we have to fix n minus k's n's, then that would decide your k positions for fixing e's. So, therefore, this is going to be equal. Anyway, we will discuss it further. So, and again we can ask this question a little slightly, make it a little more difficult. So, what about the second question, number of paths from 0 0 to 6 4, if you want to visit 4 2 on the way, right. I will go back to my picture. Here I want to reach 4 6, but the constraint now is that I want to visit 4 2 on the way. Where is 4 2? 1 2 3 4, 1 2 3 4 4 2. This is the point. Okay. Let us say 2 4 on the way. So, let's not, because anyway this looks more simple. So, 2 4 on the way, 2 4 will be this. Maybe we will take a different question and then say this time I want to say so this is 0 0. Let's see, this is 1 2 3 4 5 6 6, right. 1 2 3 4 5 6. Suppose I want to reach, sorry, 1 2 3 4. So this is the point I want to reach. Say this is actually this is actually 6 4, right, 6 4, because in the x axis I see 6 and in the y axis I see 4, right, 0.64. But now the constraint is that I have to check, I had to hit 4 2 on the way. 4 is this, 4 2 is this, 4 2 on the way. So I have to drive from here to here, but I have to make sure that I stop here on the way. So it's very clear that if I take this route, I cannot come back to here, right, I will already cross it. So many routes I will not be able to take. So how to handle this question? So first, because it's very clear that I have to hit that, so first I reach there and then from there I have to go. So now I first count how many ways to reach here, right. So this is 4 2, so I can take 4 2, so I will write it as k n minus k. So that means k equal to 4 here, n minus k equal to 2 here. So that means what is n? N is equal to 4 plus 2 6, n equal to 6, right. So now there is 6 choose 4 ways, that is what we proved before. There are 6 choose 4 ways, routes to reach from here to here. From here to here, how many ways I can reach? Now this is the same problem, because once if I look at, I will translate this 4 2 to 0 0. So then this will become because so the 2 units sorry 4, yeah, 6 will become 2 and then this will become, because it's just 2 more units here, and 2 will become 2, right. So I just want to reach from 0 0 to 2 2, right. So that is because k equal to 2 here, this is n minus k, so that is n equal to 4, right, n equal to 4. Together, adding together, that is there are 4 units to cover, and out of the 2 units should be eastward, right, 4 choose 2 ways. So 4 choose 2 ways. So to reach from here to here we have 6 choose 4 ways, and from to reach from here to here we have 4 choose 2 ways. Then by product principle, so we can multiply the ways, because I can take a route from here, so any route I can take from here to here which is valid, and then combine it with any route which is valid from here to here, right. So see, of course here I argued that you can translate 4 2 to 0 0, but it is not necessary. You can notice that from here to here, to total from where you are, you have to take 4 more units to reach here, out of which 2 units are eastward and 2 units are northward. That is all we need to know, right. So this is 6 choose 4 into 4 choose 2, right. Now another question here is number of paths from 0 0 to 6 4 such that we either visit 3 2 or 2 3. 6 4 same destination. Now this time the condition is that say, so let us say I'll remove all these things. So either I should visit 3 2 or 2 3, means it is not that 2 3, where is 3 2? 3 2 is 1 2 3 3 2 here, this is 3 2, 3 2 is this, and 2 3 is say this, right, 2 3 is this. So I should either touch this point or this point, not both. See, it is not possible to touch both, because if you are already here, then there is no way of going back to here, right. Or similarly, if you are already here, there is no way of going back to between these 2 points. So, without loss of generality you reached here first, then that means what? That means you have already crossed this line, right, and you haven't hit this, that means you are below this line. So, now you can try going forward, but you will never reach here. Similarly, if you are already here, that means you have crossed this horizontal line, you are above the horizontal line, but since you haven't reached here, that means you are below this line. So, it means before this line, and then you may try how much ever to move towards the right, towards east, but you will not be able to hit this thing, right. So, therefore, if your car is stopping here, then your car will never stop here, right. So, the paths which are going through this point is disjoint from the set of paths which are going through this point. So, the set of paths which are going through this point is disjoint from the set of paths that are going to going through this point. So, therefore, we can add according to addition principle, because they are disjoint sets. Now, we just need to know how many paths will go through this thing. Same argument, this was 3 2, 3 2 means total 3 plus 2 5 units we have to travel here. Out of that 2 should be say northward, or 3 should be eastward. So, that is 5 choose 3, right, and then from here to here 3 to 6 4, right, 3 more units in east and 2 more units, and that means 5 more units you have to travel, right. That is again 5 choose 2, because 5 choose 3, because we are in 3, we need to take 3 eastern directions, east steps. Similarly, here 2 3, that 5 unit you have to reach, out of the 2 should be taken in the eastern direction, that is 5 choose 2 to reach here, this many ways, and from here to here we have to take total again 1 2 3 4 5 units. Out of that 5 units, 4 units should be eastern, right. So, this is the number of routes going through this point, right. The number of routes going through this point is this, right. We reach here first somehow, and then from here you can reach here. So, by product principle you can find the routes which are going through this thing, this corresponds to the last problem, remember, and then through this also. Then by addition principle you can add them together to get the total number. Yes, now we will look at another question. So, here is a slightly more sophisticated counting. So, we want to this time we want to count the northeastern paths from 0 0 to n, but then we should make sure that these routes, our car never crosses the x equal to y diagonal, the main diagonal, right. So, in other words, so let us see. So, we are supposed to reach from 0 0 to n, right, something 0 0 to n. Our main diagonal will correspond to this. So, this is the main diagonal. Okay. Yeah, maybe I can, the main diagonal will correspond to this. Yeah, the n will be here. See, the point is we can hit this diagonal points, we can touch this diagonal point, but we are never allowed to go above it. I mean, a point like this is above the diagonal, a point like this is below the diagonal, right. So, we should always be below the diagonal, right. So, now we want to reach this n comma n. So, n comma n means we are n steps here and n steps here, right. Now, total 2n steps we have to travel. If you just want to find out how many paths are there from 0 0 to n, that is n 2n choose n, right, because we just have to take n eastern steps out of the total 2n. But then now we are told that we are not allowed to take some routes, those routes like this. For instance, you cannot take a route like this, starting like this, this kind of route is not allowed, this kind of route, because it is growing above the diagonal, or even this route is not allowed, right, because here you are already above the diagonal, right. So, that means this many are not available. So, now we are going to show that we are not going to count the exact number of routes here, that we will do later, but here we are going to show, this is to illustrate the bijective proof, show that this is equal to counting a certain other things, namely something like this. So, you draw a table like this. So, this is a 2 by n matrix, say 2 by n matrix or 2 by n rectangular array, right. So, there are n of them, 1, 2, 3 up to n here, this is 1, 2, 2. Now, total 2n squares are there inside this, 2n squares. Now, we are supposed to fill the squares using the numbers from this set, that means the numbers from 1, 2 up to 2n. You have enough numbers, right, exactly 2n numbers, 2n squares. So, nothing should be repeated, everything should be used exactly once. But when you fill, we have to make sure that if you read out these numbers from on a row from left to right, if you read out the numbers from on a row from left to right, that should increase, Similarly, the second row, this row also, it should increase like this. Similarly, if you read column wise, it should increase downward, okay, increase like this, it should increase like this. So, for instance, you can fill something like 2, 5, 6, 7, 8, but you cannot fill like 2, 5, 4, this is wrong, you cannot come down. Similarly, here if you have filled 7 here, then it should be 9 or 10 or something like that here, right. So, it should be a bigger number above, right. So, that is only. We ask how many ways you can fill such a rectangle using the numbers from 1 to 2n, using each number exactly once, and such that along the row the numbers increase as we go from left to right, and along columns the number increases from when we go from top to bottom, downward. Or that is only two of them, therefore, it should be in increasing order. The upper number should be smaller and the lower number should be bigger. So, we claim that the number of ways of filling this table is exactly equal to the number of ways of traveling from 0 0 in that lattice, that grid structure, to n comma n without ever crossing the diagonal. How do we see this? So, again we construct a bijection between S and T, S being these paths, that means the paths from 0 0 to n comma n which never crosses the diagonal, and T being the number of ways, the number of tableaus. This is called a tableau. After you fill it, it is a tableau, and the way we have asked to be filled, finally that such a tableau will called a standard Young tableau, right. So, So, the number of standard Young tableaus 2 by n Young tableaus. Okay. So, this will be equal to the number of paths, northeastern paths from 0 0 to n comma n, such that it never crosses the main diagonal, never goes above the main diagonal, that will be equal. So, how will you set up this thing? One thing is to look at say a northeastern path which never crosses the diagonal and show how to create a Young tableau from this thing, right. This is easy. What you do is as the driver moves on, he counts the number of steps, he keeps track of the step he is doing. So, this is the first step. So, this is the second step, this is the third step, this is the fourth step, this is the fifth step, sixth, seventh, eighth, like that. The first step he has taken in the eastern direction. So, that was an east, right. So, he write that one here. Second step he has taken in the eastern direction, because whatever he does in the eastern direction, that step number he will write on the upper row. So, 1, 2, then third step also he had made in the eastern direction. Fourth step he made in the northern direction, that you write here, right. And then fifth step here, because it was taken in the eastern direction, and sixth and seventh are in the northern direction, that you will fill here, sixth and seventh, the lower column. The lower row correspond to northern, the step numbers he has taken in the northern direction, in the order, whichever step is taken earlier will be written earlier. So, this northern direction, that means 7th, 8th, right, and say like that you will fill. So, you can see that you can fill by, because the 2 n steps you will be taking, and each step he is filling either above or below, right. And then when we have filled, so is it possible that he will try to fill some after filling the entire n squares available in the upper row, he will try to fill one more number there? No, it is never possible, because if he had entered n numbers in the upper row, that means he has already taken n steps in the eastern direction. Now, he will not take, he has already reached here, this last point, and then he cannot cross that, right. He cannot, because if he cross that, he will never reach n by n, right. Similarly, so then the rest of the things will come in only in the similarly, if we had filled n all the n squares in the lower direction, it is not possible for him to enter anything more, because nothing will come in that, because he has already reached this line, then vertically he has gone this many, in the northern direction he has gone already this distance. Now, he passes further, then he will never reach an end, right. So, any valid path will give only n numbers in this row and n numbers in this row, out of, and total 2 n numbers are there. It will be clearly giving a tableau with all distinct numbers appearing this thing and correctly filling. But the only thing, and definitely if you in a row, either in the upper row or row, we have entered the numbers in the increasing order only, there is no problem there. The only thing we have to check is will we have a conflict in the column, that means when we read one column, will it possible that the upper number is smaller than the lower number? We claim that that will also never happen, because what does this upper number means? That means upper number being say in this fifth step, right, right. In the fifth step, when he was he has already taken the fifth step, right, and right. So, when he has already taken the fifth step, now if he is going to see a smaller number here, right, 3. So, suppose you see 3 only here. That means when he wrote 3 here, right, that means in the third step. So, maybe 3 means I have already written 3 here. Let's say for a little later stage, suppose I see a 11 here, and I see only a 9 here, because I really want to show that whatever number I see here will be bigger number. Then that means 9 was entered, because 9 is an earlier step. This was entered before 11, right? At that time, right, that means right, right. At that time we were definitely above the main diagonal is what we see here, right. So, that is why that increase cannot happen, right. So, what we see is here the Young tableau comes, because what the two properties of the Young tableau has indeed happened. That means, the row is increasing and the column wise also it is increasing. So, for instance, I can show this thing by example. So, the way we have written here, the first step, right. So, it is in the eastern direction, right. So, now when I write the fourth step, right, is coming here, right. So, it was taken later, right. So, now, so it is increasing here. So, it is fourth step is coming here, right. After several eastern steps only we are already quite so we are here, right, by the time we first entered here. So, then therefore, we will be below the main diagonal, right. Similarly, to second when I am seeing, so then I am seeing a 6 here, because we again went one more step here, we put it here, and then the 6th is coming here. That means, we are already here, and that is why we are below the main diagonal. Only 2 steps are going to the northern direction, that is why. So, this is increasing only, right. So, like that we can check. So, now it is time, we will explain it further in the next class.